SN1 is a first order reaction. With SN1, it's completely different than SN2 in terms of mechanism, although the product is going to be the same. The conditions of the reactions are different and the mechanism is different. So with SN1 reaction, it is a two-step reaction. You start with the first step in there, and the first step is a slow step. So this is the step that you determine the rate of the reaction. You start with the alkyl halide, the leaving group leaves on its own and it creates a carbocation. After you create a carbocation, the carbocation will be an intermediate. Then the nucleophile is going to attack the carbocation in a nucleophile electrophile reaction in order to get you to your product. The nucleophile cannot react in the first step because the nucleophile for SN1 is weak. It's different than the nucleophile that we used for the SN2 reaction. That was a strong one. This is why it could react at the first step. But here the nucleophile is weak. It cannot react. So this is why you would need to allow the leaving group to leave and form a stable carbocation. Once you form a stable carbocation, then the nucleophile is going to attack and your reaction is going to proceed by two steps, two total steps. The solvent that you're using is a polar protic solvent, and you need the solvent because this solvent is going to gather itself around the carbocation and it's going to stabilize the carbocation as the reaction is happening between the nucleophile and the carbocation. So as we mentioned, the rate of the reaction depends always on the slow step. And the slowest step in the reaction is always the step where you're not forming your product. The step that you form your product is a fast step. So the second step here is a fast step. But the first step when you're forming the intermediate is a slow step. So it's this step that you determine the rate of the reaction. So the rate here depends on the concentration of the reactants, and the reactants are only alkyl halide or alkyl leaving group. So it only depends on the concentration of the alkyl leaving group, meaning that if I change the concentration of the nucleophile, nothing is going to happen to the rate of my reaction. For the conditions of the SN1 reaction, the first thing is the alkyl leaving group. The alkyl leaving group has to be a tertiary alkyl leaving group. It can work with secondary, but the reaction cannot work with primary and the methyl leaving group. It is a two-step reaction, and it proceeds by formation of the carbocation intermediate. Carbocation is whenever you're leaving a group leaves and you end up leaving or having just the carbon with a plus charge. Tertiary carbocations are more stable than secondary, than primary, than a methyl carbocation. Primary and methyl, they do not exist. You cannot write a primary carbocation in there. Now, the reason for the stability of the carbocations is because the distribution of the charge. CH3 is an electron donating group. Why it's an electron donating group? Because the carbon is an sp3 hybridization and the carbocation is an sp2 hybridization. We know that sp2 are more electronegative than sp3. So sp2 will steal electrons from the sp3, making the sp3 donate electrons. So see, this carbon here has a plus charge, meaning that it is an electron deficient site. But because it's an electron deficient site here, it's taking electrons away from the other sp3 hybrid carbon so that all of these carbons share the electron deficiency, and the electron deficiency is not just concentrated on this central carbon. That is going to increase the stability of the carbocation. So here the carbocation is stabilized by inductive effect, and the inductive effect is simply the process of pulling the electrons through the sigma bond. I have here three electron donating groups. They will donate electrons to this carbon positive so that they will distribute the electrons across the whole structure instead of making the central carbon being just electron deficient. Versus, on the other end, I have here two electron donating groups. Versus here, I have one electron donating group. So see, the more electron donating group around the carbocation, the more stable the carbocation is. And again, it is stable because I'm distributing the charge, and the charge is not just focused on the central carbon. Primary carbocations and methyl carbocations, they are completely unstable, so they do not exist. You cannot make them. So this is why you cannot start from a primary alkyl halide or a methyl halide. After all, these carbocations are made whenever each one of those loses a leaving group. So when tertiary alkyl halide loses the leaving group, it's going to make a tertiary carbocation. When the secondary alkyl halide loses the leaving group, it's going to make the secondary carbocation. So those two, they have no reaction because the carbocations are completely unstable. They do not exist. Now, every time you make a carbocation, you need to form the most stable carbocation, because the idea here is that I am forming the carbocation as an intermediate, and the nucleophile is attacking that carbocation to make my product. So the carbocation that I am forming has to be a stable carbocation. To be a stable carbocation, we said that tertiary carbocations, they are more stable than secondary carbocations. We're not going to talk about primary and methyl because they don't exist. Meaning that whenever you have a secondary carbocation, you need to ask yourself this question: can I make it tertiary? So you need to form the most substituted carbocation possible so that the intermediate is a stable intermediate so that you can form your product. So this is going to take us to a reaction which we call rearrangement that SN1 intermediates undergo. The intermediates are carbocations, and every time you form a carbocation in any organic reaction, whenever your intermediate is a carbocation, carbocation tend to rearrange and form a more stable carbocation. The rearrangement happens from a secondary carbocation to a tertiary carbocation, and it happens by two methods: either by moving a hydrogen or moving a CH3 in case the hydrogen was not there. Rearrangement cannot happen from a primary carbocation to a secondary or tertiary because primary carbocations, they do not exist. So the rearrangement only happens in case you have a secondary carbocation and you want to form a more stable carbocation, which is a tertiary. If you're doing the reaction and you get a tertiary carbocation, then you don't need any rearrangement because the tertiary carbocation is a very stable carbocation. The nucleophile that we use in this type of reaction is always weak nucleophile, so it's a neutral. Solvent is polar protic solvent. And for the stereochemistry of the reaction, every time in SN1, we're going to end up getting two products. One product is going to be inversion in configuration, and the second one is going to be retention. So if we combine both of these, they're going to be racemic mixture. So the products of SN1 are always both. If you combine them, they are optically inactive. Let's have an example over here on the rearrangement of the carbocations. So I'm starting with my secondary alkyl halide, and I am showing the stereochemistry of my leaving group. So if you're showing the stereochemistry of the leaving group, you need to show the stereochemistry of the product. Okay. My nucleophile here is the water. Water is a neutral nucleophile, so water is going to go by an SN1 reaction. Whenever you're using water, and this is especially for SN1 reactions, neutral nucleophiles also act like solvents. So I can use this nucleophile as a nucleophile, and whenever I want to use it as a solvent, I will use it as a solvent. So I don't need to put a solvent in here. Or if I want, I can go ahead and put a polar protic solvent. But if I put a polar product solvent in here, always the first reagent that I use is going to be the nucleophile. The second one is going to be the solvent. But as I said, with SN1 reactions, because we are working with the neutral nucleophiles, those neutral nucleophiles act as both as a nucleophile and as a solvent. With SN1 reaction, there is a role for the solvent. The solvent always, and these are especially polar protic solvents, not polar aprotic solvent. Polar protic solvents always, they act as a base at the end of the reaction. So these, they act as a base at the end of the reaction, always. So if there is an extra hydrogen in the solution, they are going to come and take the extra hydrogen. So they're going to act as a base to take the extra hydrogen in there. This is why in SN1 reaction, it's so important to have a solvent, because always you want your product to be neutral and you don't want your product to have a charge. And with SN1 reaction, you're always going to go down to the last step. And in the last step, you're going to end up having a positive charge in your product. So you would need a solvent to act as a base to take the acidic hydrogen to make your product neutral. So let's go ahead and do the mechanism for this reaction here. You have to show stereochemistry, as I said, because your leaving the group is shown as a stereochemistry, and you have a chiral center. First step with SN1 reaction, always it's two steps in there. It can be more if you are doing rearrangement, and we're going to have an example of rearrangement. So the first step, the halogen is going to leave. Once the halogen leaves, you're going to create a carbocation. Now, when you create a carbocation, you have to check what is the type of that carbocation. And this carbocation is connected to two carbons, two carbons here. So this carbocation is a secondary carbocation. The moment you see a secondary carbocation, just ask yourself, can I make it more stable? Meaning, can I make it a tertiary carbocation? The process is called rearrangement, and rearrangement happens by either moving a hydrogen, an adjacent hydrogen, or moving a CH3. If the adjacent hydrogen is available, then please move the hydrogen. So here, I have two adjacent hydrogens. I have an adjacent hydrogen on this adjacent carbon, okay? And I have an adjacent hydrogen on this adjacent carbon. If I move this hydrogen, then my plus charge is going to be here. It's still secondary, as if I did nothing. But if I take this hydrogen together with its sigma bond, so together with its electrons, and I move it here, now my new plus charge is going to be tertiary. This is more stable than that. So this here is a process which we call rearrangement. So rearrangement by a hydrogen, or by a methyl shift. You look at the adjacent carbon to the positive charge. You circle the hydrogen together with its sigma bond, together with its electrons, and you move it towards the carbocation. You create a new carbocation. The new carbocation that you create has to be more stable than your original one. Then it's this one that you're going to use and continue the rest of the mechanism. So in the step 2 now, I'm going to take my tertiary carbocation, not my secondary, my tertiary carbocation. And now I'm going to go ahead and react it with the nucleophile. Notice, as we mentioned before, that the nucleophile is a weak nucleophile. It's a neutral, so it's weak. Because it's weak, it could not attack from the beginning. This is why I wanted my halogen to leave. I wanted to make a carbocation. I wanted to stabilize the carbocation. After I formed a very stable carbocation, now my weak nucleophile is going to attack. In chapter 1, we've talked about the hybridization of the carbons. So this carbon is planar because it is an sp2 hybridization. It has three groups around it. So it is an sp2 hybridization and it is planar. All the bonds here, they lie in the same plane. So when they lie in the same plane and you have your nucleophile attacking, you have two ways for the nucleophile to attack. The nucleophile can attack either from the top or it can attack from the bottom of the carbon because all of those they lie in the same plane. So the nucleophile here attacks from the top or it can attack from the bottom. To show that the nucleophile is attacking from the top, simply use the wedge line. So here water is attacking from the top. And notice what I am doing here. I am making a bond between the oxygen and the carbon. So the new bond that I formed here is a bond between the carbon and the oxygen. I am adding the whole nucleophile with its oxygen there and the two hydrogens. So add everything in there. Okay, so this is it. Or the nucleophile can attack from the bottom. So I'm going to say plus in there. This is the second possibility and show the water attacking from the back. If the water attacks from the back, that's going to push the CH3 to be in front. And if it's attacking from the front, that's going to push the CH3 to be at the back. Now, let's pause here for a moment. This cannot be our product because our product should always be neutral. It shouldn't be a plus charge. And this is what I was saying, that every time you're using an SN1 reaction, you need a solvent, a polar protic solvent, to act as a base so that it can take any extra hydrogen in the solution. This step is called a deprotonation step. Deprotonation is the loss of hydrogen. So now water, I can use water again or any base in the solution. But here the only base that I have in the solution is water. Water is more basic than the Cl over here minus. So this is why I am using water. Water is going to come and it's going to take both of these hydrogens in there in both products. And you're going to end up getting the neutral product, which is the OH. So it's as if water added to the carbocation in a form of an OH and not water. So this is going to be my product in this case. Do the configuration for each of the chiral centers over here. So I have a chiral center here and I have a chiral center there. Do the configurations for each of these chiral centers and do the configuration of the reactants. So this is going to be my reactant here. Let's do the configuration for this chiral center. I have my hydrogen here. So I'm starting with group 1. This whole thing is going to be group 2. This is priority 3. And the hydrogen is already behind. So I am going by 1, 2, and 3 like that. And this is going to be clockwise. So it is an R configuration. I'm just going to keep it an R because I didn't do anything to the hydrogen. It's behind. I didn't switch anything. So here it's an R configuration for this chiral center over here. In my product, I'm going to end up getting two products. One of them is going to be R configuration for the chiral center. We are going to call this retention, meaning that the configuration stayed the same. And the second one is going to be inversion in configuration. This means that the configuration is inverted from the original chiral center. You started with a chiral center that is R, you ended up with a chiral center that is an S, and another chiral center that kept its configuration to be an R. So you get inversion and retention in configuration. So every time you are working with SN1 reaction, you're going to end up getting two products in there. Those two products, if you combine them together, they are racemic mixture. There is a rule, and the rule states that if you're doing a reaction and you start from the reactants and your reactant is optically inactive, then your product has to be optically inactive. Here I'm starting with my alkyl halide. Alkyl halide here is optically active. But when I reached those products here, I started from the second step. And from the second step, I have a carbocation. This is not a chiral center. So this is optically inactive. So it's considered to be the reactants for the final products. So if the reactant is optically inactive, then the product has to be optically inactive. This is the rule for reactions. And here it's optically inactive because if you combine them both together, it is a racemic mixture, and racemic mixtures are optically inactive. Okay. Now, of course, when water takes the hydrogen, it's going to become H3O plus in there. So you have also to write it down. Let's have another example where we are doing rearrangement with a methyl shift. So again, I am having a chiral center over here. So you're having a chiral center, and I'm showing the configuration on that chiral center, iodine being behind and the hydrogen here being in front. Okay. My reaction is proceeding with a secondary alkyl halide, a weak nucleophile because it's a neutral. Now see, this is the nucleophile. Now I have a solvent in there. Whatever reagent that comes first is always your nucleophile. So if you're looking at the NH3 and water and asking which one is the nucleophile, which one is the solvent, whatever comes first is the nucleophile. So whatever comes first is the one that you are adding to your product. So at the end, your product should have NH2 in it. Okay. Water is going to act as a solvent. And as we said, in SN1 reaction, the role of the solvent is to make sure that your products are always neutral. So solvents at the end, in the last step, they act as a base and take the extra hydrogen in the solution. So the first step here, you are going to lose the iodine. This is going to be the first step. So iodine is lost, and you're going to make your carbocation in this case. The carbocation is a secondary carbocation. Now you're going to pause, and you're going to ask yourself, can I make it more stable? To make it more stable, you have to look at two adjacent carbons. You have an adjacent carbon here, and you have an adjacent carbon in there. If you move the plus charge here, then it's going to be secondary, as if you did nothing. But if your positive charge is moved here, then it's going to be a tertiary carbocation. Why tertiary? Because this carbon has no hydrogens in there. And you can only move a CH3. You cannot move a hydrogen. And you always do a methyl shift or a CH3 shift whenever you don't have a possibility of moving a hydrogen. Then you go ahead and you move a CH3. So here, the only thing available is taking the CH3. So we're going to circle the sigma bond together with the CH3 and move it towards the plus charge. Then we're going to end up getting our carbocation in this case, and that carbocation is connected. See to how many carbons it's connected. It's connected to 1, 2, and 3 carbons. So now it is a tertiary carbocation. This is after the methyl shift. It's this one that is more stable than whatever I had. So it's this one that I'm going to use in order to get to my product. So you take your carbocation now and you react it with the nucleophile. We agreed that NH3 is the nucleophile and the water is the solvent. So the NH3 now is going to come and add. And please remember that SN1 reaction always have two products. SN2 reaction always have one product. So the NH3 in this case is going to attack from the top and from the bottom. Reason why? Because the carbon, the carbocation here, is an sp2 hybrid carbon, which is a trigonal planar geometry. So you're going to end up having your NH3 being in front or can be behind. Your formal charges are very important. When nitrogen has 4 bonds, it's a plus a charge. So now you know that you cannot have a product that is charged. Your product is always going to be neutral. So now this is the role of your solvent. You take your solvent, and that solvent, you are going to use that as a deprotonation step. So your solvent here is going to be water. You can use another molecule of NH3 if you want. But since the solvent is there, you can use the water. Let's say, for example, if water is not there, then the NH3 is going to act as a solvent in the last step. So with SN1 reaction, the nucleophile always acts as a solvent in case the solvent is not present. And the role of the solvent in SN1 reaction is to ensure that the final product is neutral. So the solvent always acts as a base to take out the extra hydrogen in the solution. The solvent will not appear in the organic product. So your organic product will not have an OH in it. Your organic product will have the nucleophile in it, which is the nucleophile minus the hydrogen. So it's going to be an NH2 in there. Notice that the highlighted carbon here is not a chiral center. So if it is not a chiral center, I don't need to show stereochemistry to start with. So this is why I'm going to switch those two over here to a solid line. No need to show stereochemistry. And then use the solvent in there, which is water, in order to take the hydrogen, the extra hydrogen is going to act as a base, form the lone pair on the nitrogen, and now I'm going to get my product here. I don't have a chiral center in my product. So let's take this out. There is no chiral center in there, so I'm going to end up getting only one SN1 rearranged product since there is no chiral center. If I'm starting with a primary alkyl halide and using a neutral nucleophile and a polar protic solvent, those two are the right conditions for an SN1 reaction. However, the primary alkyl halide is not the right condition because I cannot make a primary carbocation. So this is why I'm going to end up having no reaction. Let's have another example here. Starting with a secondary alkyl halide, I'm using a weak nucleophile and I'm using my solvent. As I said, the first reagent that you see is going to be your nucleophile. The second one is going to be your solvent. Not every time you're going to see a solvent in the SN1 reaction. If you don't see a solvent, then use the nucleophile as two roles, as a nucleophile, and in the last step, use it as a solvent. Now, if you have a nucleophile and a solvent, you can see it in many different ways, written in many different ways. You can see the methanol and the water written like this above and below the arrow. The methanol is going to be the nucleophile, and the water is going to be the solvent in this case. So this one is going to be the nucleophile, and water is going to be the solvent. And you guys, always your nucleophile is always at the beginning. So you start with your nucleophile every single time, and whatever comes next is going to be your solvent. Or you can write it next to each other like that. So if you have it like this is going to be the nucleophile, this is going to be the solvent. So your product is going to end up having the nucleophile in it. So here, the bromine will be replaced by the OCH3. We agreed that since it's a neutral nucleophile, when you replace it, when you replace the bromine with it, you are going to lose a hydrogen every single time from a neutral nucleophile. So in reality, you're adding an OCH3 at the end. If you are creating a chiral center at the end, you're going to end up getting two products. So let's see over here. We are starting with our secondary alkyl halide. So starting with the secondary alkyl halide, step one, bromine is going to leave. You create a carbocation. Now this carbocation is a secondary carbocation. That secondary carbocation I cannot rearrange because you just imagine if you move the positive charge to this adjacent carbon, you're going to end up getting a primary carbocation which is less stable than the secondary. You cannot do that. And if you move that positive charge here, you're going to end up getting still a secondary carbocation. So what's the point? You leave it as is in this case. So there will be no hydride shift. There will be nothing in there. Now, once you have your carbocation, then you take that carbocation in the second step and you allow the nucleophile to attack from both sides in there. Now notice that you are starting here, as we mentioned, with an achiral compound because the compound has no chiral center. So by definition, if you start with an achiral compound or an optically inactive compound, then your products need to be optically inactive even though they have chiral centers. So they will be a racemic mixture in this case. So you get the two cases, the attack from the top and from the bottom. And your OH is going to be attacked from the top, from the bottom. Now here I am creating a chiral center. So please go ahead and do the configuration for that chiral center. And do the configuration of your starting material. So the chiral center here is an S. So one of my products need to be the same configuration. This is going to be the retention. The other one is going to be the inversion in this case. However, my product has to be optically inactive because I am starting with a carbocation to reach this product and it is optically inactive. So this is why I combine both two and I say that my product is going to be a racemic mixture in there. Before I missed a step here, which is the deprotonation step. So do the deprotonation step here, which is the final step before you go ahead and you combine both products and say that your product is a racemic mixture. So the deprotonation step here, you can use either methanol or water, whatever you want, because both are neutral and both are bases in there. In normal cases, since water is a solvent, we use the water. But if water is not there, as we always say, you're going to go ahead and use the methanol in order to do the deprotonation step. So go ahead and use the either one of those. Take the extra hydrogen, and you're going to end up getting your two products in this case. So the two products here are going to be the inversion one, and they're going to be the retention one. This is going to be 50% R, 50% S. This is why what I'm going to do is I'm going to combine both together and I'm going to say that my product is optically inactive. You're always going to form a racemic mixture if your products have chiral centers because, again, they are derived from a carbocation which is optically inactive. If your reactants are optically active, then your product should be optically active. But your product in SN1 can not be optically active because you are always going to derive your products from the second step. And the second step involves the formation of the carbocation. And carbocation is not a chiral center to start with. Let's have another example over here. So we are starting with a secondary alkyl halide. This is going to be your alkyl halide. And we have a secondary alkyl halide, a neutral nucleophile, and polar protic solvent. So everything here tells me that it is an SN1 reaction. Step one, my halogen is going to leave. I'm going to make my carbocation. Once you make your carbocation, you guys, look at the adjacent carbons. You do have two adjacent carbons here, this carbon and this carbon. So if you look at the adjacent carbons, move the plus charge. If you move the plus charge here, you're still going to end up getting a secondary carbocation. But if you move the plus charge here, you're going to end up getting a tertiary carbocation. So you can go ahead and move it over here by doing a hydrogen shift. You don't do a methyl shift. You have two options here, either moving a hydrogen or moving a CH3. But you never ever move a CH3 if the hydrogen is available. You can move a CH3 if the hydrogen was not there. So if instead of the hydrogen you had a CH3, then yes, you can go ahead and move a CH3. But if you had a hydrogen, please move the hydrogen because hydrogens are smaller atoms and they can be moved faster than the CH3. CH3 is a molecule. So you move the hydrogen, and again, you circle the hydrogen together with its sigma bond, 2 electrons, and you move it towards the plus charge. So the hydrogen now is going to be in the place of the plus charge, and you're going to create a new carbocation on that carbon. Once you create your new carbocation, it's this carbocation that you're going to take because it's more stable than the secondary, and you're going to proceed with your reaction. So this one, go ahead and react it with the nucleophile. Don't be afraid of the nucleophile and how big the nucleophile is. The rule is a rule. You choose the nucleophilic site of the nucleophile, and you start your arrow from the lone pair of the nucleophile towards the plus charge. So you are making a bond between this carbon and the oxygen. This is what you're doing. So you're making a bond between the carbon and the oxygen. On the oxygen, you have a hydrogen. It's this hydrogen. And on the other side, you have a carbonyl connected to the CH3. Please write everything down. Don't take out anything that is related to the nucleophile. Write everything in there. The acetic acid is going to attack either from the top or from the bottom. So show it as attacking from the top and attacking from the bottom. That's going to push the CH3 to the back or to the front. After you do this, please do the deprotonation by any solvent that is present in the solution. It's going to act as a base, take out those 2 hydrogens in there. This is still a chiral center, so do the deprotonation and you're going to end up getting, in this case, the 2 products. These 2 products are going to be inversion and retention in configuration. Those 2, you combine them together and you say that the product is a racemic mixture and it is optically inactive. SN1 reaction is a 2-step reaction. So we need to show this in the energy diagram. To show this in the energy diagram again is the plot of the energy versus the reaction coordinates, which is the time required for the reactants to go into the products or to reach the products in there. The reaction here is 2 steps. The first step is the slow step where you form your intermediate. So carbocation is the intermediate. And by definition, intermediate is the product of the first step and the reactants of the second step. So this guy over here is our intermediate of the reaction. Intermediates are not products. So we expect the energy to make those intermediates to be higher than that of the energy of the final product. The energy of the final product needs to be low so that the reaction can proceed towards the product. So you're starting with your reactants. You've passed by your first transition state. What is the first transition state? The first transition state from the step 1 is when the carbon bromine bond breaks. And to represent the carbon-bromine bond breaking to form the carbocation, you just represent it as a dotted line. This is going to be your transition state 1. Now, transition state 2, you are showing that you're forming a bond between the oxygen and the carbocation. So you're going to show the bond formation between the oxygen and the carbon. This is going to be transition state 2 in there. Because the second step is the step where the product is formed, this step over here is going to have a lower energy than that of the first transition state. So transition 2 is going to have lower energy. Remember that energy and stability are related. So the higher the energy, the less stable the product is. The lower the energy, the more stability you have. So over here, this is going to be more stable transition 2 because it is starting to get to the product. Remember that the lower the energy, the more stable the product is. Transition state 2 is lower in energy, and we want it to be lower in energy because we are starting to get to the product. So with the transition state 2 over there, these two are going to react with each other. This is it's their transition state, and you're going to end up getting your product. Your product always should have a lower energy than that of the reactants. So that delta H is negative, which is exothermic. Now, if I ask you which step is the slowest step, you need to compare the activation energy of each one of them. So the activation energy between the reactants and the transition state for the first step, and the activation energy between the reactants, which is the carbocation, and the transition state 2 of the second step. You would see that the activation energy here is smaller than the activation energy there. So if it is smaller, this means that this is a faster reaction. And it needs to be fast because this is the step where you are forming your product. This is why whenever we are working with the rate of the reaction to measure it, you need a slow step to measure it. So this is why we say that the rate depends only on the concentration of the alkyl halide, because it's this step that we use to measure the rate of the reaction.